Good morning. In the last class, we started to study about the classification of defects based upon dimensionality. And we classified three types of defect: a zero-dimensional defect, a point defect, one-dimensional or line defect, two-dimensional or surface. In this syllabus of basics of material science, we will be focusing ourselves only up to the point defect. So next heading we are going to put is point defect. A point-like region is imperfect, means the size of the defect is not more than 1 or 2 atomic diameter. At max, the size of the defect should be equal to 1 or 2 atoms, not more than that. So such kind of defects are known as point defect. Good morning everybody. I am reading your messages. Thank you for your well wishes, and let's continue for studying this class. I'm feeling better. Right. So here let's talk about a point-like region. A point-like region is imperfect. The size of point defect should not be greater than 1 or 2 atomic diameter. So size of the defect is approximately 1 or 2 atomic diameter. A point defects can further be classified as point defects can be classified as first, vacancy defect. What is this? Have a look. Let us suppose we have whole atomic arrangement like this. These are the atoms. These are the atoms. Now, 1 or 2 atoms are missing from the crystal. Suppose 1 or 2 atoms are missing from the crystal like this. So such vacant atomic site is known as a vacancy defect. Means there should have been atom. This is a lattice point. Lattice point means the point, a three-dimensional periodic arrangement at which atoms should be located. So there should be an atom, but due to any reason the atom is missing from that place. So that vacant atomic site is creating a vacancy defect. So this is vacant atomic site. Vacant atomic site. An atom is missing from its lattice position. An atom is missing from its lattice position, and hence a vacancy defect is created. A vacancy defect is created. And hence a vacancy defect is created. An atom is missing from its lattice position, and hence a vacancy defect is created. It is a strong function of temperature. As you increase the temperature, then bonds may be broken. And if the bonds are broken, some atom may acquire thermal energy and it may move from its place to the another place. Once the atom is moving, so at that place you will get a vacancy. Hence, with increase in temperature, this kind of defects will increase. Again I am telling you, with increase in temperature there will be possibility of breaking up the bond. So if any bond is broken, then the atom will become free, and that atom may move from its place to the another place. So from where the atom is moving, at that point you will get a vacancy defect. So with increase in temperature, this kind of defect keep on increasing. With increase in temperature, vacancy defect increases. Vacancy defect increases. With increase in temperature, vacancy defect increases. The second one is interstitial defect. The second one is interstitial defect. What is this? Have a look. Let us suppose these are the parent atoms. Parent atoms means the atoms of that material regarding which we are talking. Let us suppose these are iron atoms. So all these atoms are of equal size. These are places where atoms are located. These points are known as lattice point. Apart from lattice point, these spaces like this, they are known as interstitial position. The position between the two lattice point, that is known as interstitial position. Suppose a material is added into this material, which has atomic size very small comparison to these atoms. Suppose these are iron atoms and we are adding carbon atoms. So if we add carbon atoms into the iron atoms, so being very small in size, that carbon atom may occupy an interstitial position. Now at this place, periodic order has been disturbed, and I told you whenever there is change in periodicity or order of the crystal, then a defect is found. So such kind of defect is known as interstitial defect, because the impurity atom are sitting at the interstitial position. This is not the regular lattice position. Regular lattice position is this, this, this and this. It is the position between the regular lattice positions. So this space will be very less. You can assume like this. These are the atoms. This is one atom, this is another atom, this is another atom, and this is another. So this position is your lattice interstitial position. Suppose any atom is occupying this place. So such kind of defect is known as interstitial defect. This defect is found only if the impurity atom is of smaller size than the parent atoms. If impurity atom is of larger size, then such kind of defect cannot be found. So you can write it is interstitial atom. Interstitial atom. When an impurity atom of a smaller size is added into the material, then it may occupy an interstitial position, interstitial site, and hence an interstitial defect is formed. Interstitial defect is formed. Defect is formed. Next, एग्जाम्पल के तौर पर when carbon is added into iron, carbon is added into iron, it forms interstitial type of defect because size of carbon atoms is very small, as compared to iron atoms, ठीक है, पहले इतना लिख लें फिर थर्ड क्लासिफिकेशन की तरफ चलेंगे. प्लीज नोट डाउन दिस फ्रॉम पॉइंट डिफेक्ट. Ankush, yes, you should attend today's class. All the mechanical people should attend today's class, because after the point defect, whatever I am going to discuss, that is not discussed in your regular mechanical branch material science. So all the mechanical people are advised to attend the class, because we just a half an hour, after half an hour we would be starting the electric properties of material, and that is very important chapter. In last 6 years you may have got more than 9 questions from that topic. So please be there. Even in the defects of what we are going to discuss, that has not been discussed in your regular material science. So I will suggest that please everyone from mechanical or any other branch, they should be in the class. No, Assis, chromium is not interstitial in Ruby. Chromium forms a substitutional defect, the next one which I would be telling you. Nothing has been dictated. This is the first heading we started. Everything is written on the board. This is the first slide. रमन, सेमीकंडक्टर्स तो नहीं शायद स्टार्ट हो पाएगा, बट कंडक्टर्स जरूर स्टार्ट होगा. मींस इलेक्ट्रिकल प्रॉपर्टीज वी आर गोइंग टू डिस्कस. Done? I'm feeling better now. Thank you. Yes, carbon into iron is an example of interstitial defect. बिल्कुल ओमकार, you are 100% correct. Third one, suppose we are adding impurity which is of equal size, not exactly equal, of comparable size. Exactly equal to same material हो जाएगा. So if the impurity is of the comparable size, let us suppose there is difference of only 10 to 15% of the radius between the host atom and the impurity atoms, then interstitial defect cannot be formed because interstitial space are very small. So in that case, what will happen? Impurity atom will substitute any parent atom, any host atom, and this way a substitutional defect is formed. So the third one is substitutional defect. Third is substitutional defect. Let us suppose this, 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 this. Let us suppose these are the parent atom. Suppose this is copper and these are the atoms of copper, and you are mixing a nickel into the copper. So both are of almost same size. So nickel will replace to the copper, and this way a substitutional defect is formed. This is substitutional atom. This impurity atom is known as foreign atom, and these atoms in which this impurity is added, they are known as parent atom. When an impurity atom of comparable size is added, then it replaces host atom, and hence a substitutional defect is formed. A substitutional defect is formed. When nickel is added into copper या zinc is added into copper, then it forms substitutional defect. So these are the three broad classification of point defect. First one, vacancy defect, second one, interstitial defect, and third one, substitutional defect. So these three are the broad classifications of the point defect. आई एम गुड. सूरज, थैंक यू. मुझे तो लगा सूरज तुमने क्लास छोड़ दिया होगा. यू आर डूइंग क्लास, दैट्स ग्रेट. रिटन, प्लीज डू इट क्विकली. थोड़ा सा मैं रिक्वेस्ट करूंगा कि प्लीज लिटिल बिट इंक्रीज योर स्पीड ऑफ राइटिंग, बिकॉज लॉट्स ऑफ कंटेंट आई हैव टू डिस्कस, लॉट्स ऑफ थिंग्स आई हैव टू डिस्कस, and we have very less time in this subject. The subject is very wide, so we need a little bit more speed from your side in order to cover the maximum things. Yes, host atom or parent atom is same thing, means the material in which you are adding the impurity. Point defects may further sorry sorry point defects may be further classified as point defects can further be classified as, first one is stoichiometric defect, and the second one is non-stoichiometric defect. Non-stoichiometric defect. So point defects can further be classified as in two broad categories. First one is stoichiometric defect and second one is non-stoichiometric. That's good, Suraj. That's the attitude which will make you winner. Even after the heated argument, you are still to cool down yourself. And that is the quality required to become an officer. Even if you don't like anything, still you understand the value of the thing and you try to do the class. That's good. And that is the attitude one required to win these competitive examinations. I appreciate. अर्पित इज राइटिंग, सर हम लोग हिंदी इंग्लिश की वजह से क्लास नहीं छोड़ते सर, वी आर मैनेज ऑल अबाउट द थिंग्स. गुड अर्पित, दैट्स द गुड एटीट्यूड. इवन आई लाइक हिंदी, आई एम फ्रॉम हिंदी स्पीकिंग बेल्ट और मेरी 12th तक की पूरी पढ़ाई हिंदी से हुई है. मैंने हिंदी मीडियम से पढ़ाई की है. मैं हिंदी में कविताएं लिखता हूँ, मुझे हिंदी बहुत पसंद है. But these are the professional limitations sometimes. Raman is asking, sir, अगर GS के कुछ ही सब्जेक्ट करने हो तो कौन कौन से करने चाहिए? First two subjects which must not be skipped, they are maths and aptitude. मैथ और एप्टीट्यूड तो कंपल्सरली करना ही करना है, उसको स्किप नहीं कर सकते हैं क्योंकि उसका वेटेज भी लगभग, वेटेज तो चलो पेपर 1 में सभी का 5 से 15 के बीच में कहीं भी वेरी कर सकता है, बट दैट विल हेल्प यू टू इन गेट एग्जामिनेशन. और मैथ और एप्टीट्यूड एक ऐसी चीज़ है कि एवरीवन कैन बी कंफर्टेबल इन दैट, खासतौर पर जो इंजीनियरिंग बैकग्राउंड से जुड़े हुए लोग हैं. दूसरे सब्जेक्ट ब्रांच के हिसाब से चुनना चाहिए. जैसे इफ यू आर मैकेनिकल पर्सन देन यू मे बी फीलिंग गुड with project management and that quality control, standards of quality control, these two subjects you may be feeling better, and 30-40% of the material science, that may be good for the mechanical persons. But if you are a civil person, you may feel difficulty with the material science, and but still project management is good for you. And quality control is also good for you because at some places you use in your engineering branch. If you are electronics or electrical background person, you may be feeling better connectivity with the ICT, information and communication tools, material science, 50 to 60% of the material science, not 50% but 40% of the material science. So likewise, according to your branch and according to your comfort level, figure out the subjects which are static in nature, which does not have much dynamism. डायनामिज्म से मेरा मतलब है कि जो करंट अफेयर्स से बहुत ज़्यादा जुड़े हुए ना हो, क्योंकि करंट अफेयर्स से रिलेटेड चीज़ों में थोड़ा अनप्रेडिक्टेबिलिटी ज़्यादा होगी एंड उसकी वजह से समटाइम्स इशूज मतलब आपको हो सकता है कि आप पढ़ाई पूरी करें और क्वेश्चंस अच्छे से ना हो पाए। तो मेरा ये कहना रहेगा कि जो स्टैटिक सब्जेक्ट हैं, जिनका करंट अफेयर्स से टच थोड़ा सा कम है, उन पे ज़्यादा फोकस करिए। दे मे बी मार्क फेचिंग। बाकी तो जीएस में जितना वाइड कवरेज करेंगे आप, उतना बेहतर रहेगा आपके लिए। तो एक बार के लिए तो सारा पढ़ना चाहिए। आइए स्टिकियोमेट्रिक डिफेक्ट की बात करते हैं। स्टिकियोमेट्रिक डिफेक्ट। फर्स्ट ऑफ ऑल लेट अस ट्राई टू अंडरस्टैंड व्हाट इज स्टिकियोमेट्री। सिविल वाले तो जानते होंगे, एनवायरमेंट में पढ़ते हैं। Let us suppose we have NaCl. This is a solid. So in this solid, the chemical formula is predicting us that the ratio of Na plus NCl minus must be 1:1. Yeah, suppose we have calcium fluoride CaF2. So this chemical formula is telling us that the ratio of cation to anion must be 1:2. So stoichiometry is the condition where the ratio of cation to anion remains the same as predicted by the chemical formula. केमिकल फार्मूला जिस तरह से प्रिडिक्ट कर रहा है, यानी 1:1 या 1:2 जो भी प्रिडिक्ट कर रहा है, अगर वही रेशियो कैटायन और एनायन का मेंटेन्ड है, तो हम लोग कहेंगे कि मटेरियल स्टिकियोमेट्रिक है। So stoichiometry may be said as a condition where the ratio of cation to anion remains the same as predicted by the chemical formula. Right? Agreed. Now you see, my dear friend. Suppose a defect is formed. So due to defect, maybe atoms are missing from the material. For example, earlier, let us suppose I am talking about NaCl. So suppose you have 100 cation and you have 100 anion. So if any defect is formed such that कि 99 cation बचे हैं, 99 anion बचे, so although vacancies has been created because atoms are leaving the material, so there would be vacancy, a defect is formed, but you see the ratio is still 1:1. So such kind of defects where this ratio remains intact even after formation of the defect, that defect is known as stoichiometric. एक चीज और ध्यान रखिए कि no matter what kind of defect is formed, crystal must be electrically neutral. Because if it is not neutral, it will not be stable. In the very beginning, I told you that for the stability, neutrality is compulsory. Suppose some positive charge comes onto the material, then it will not remain stable. It will try to attract negative charge and try to make a compound. So it will not remain the same thing regarding which we are talking. It will become some different compound. So what I am wanting to tell you that any kind of defect may be formed in the material, but neutrality should not be changed. Charge neutrality must be maintained. कैसे होगा, that we would be watching it here later, but पहले stoichiometry define कर लेते हैं. Let us first define stoichiometry. What is stoichiometry? अंकुश हिज सजेशन इज गुड, बट वेटेज का तो मैं नहीं कह सकता। ये चारों सब्जेक्ट मैथ, एप्टीट्यूड, मटेरियल साइंस, एनवायरनमेंट, इसमें क्वालिटी कंट्रोल भी ऐड कर लीजिए आप, क्वालिटी कंट्रोल भी इसी में ऐड कर सकते हैं। सो ये सब्जेक्ट ऐसे हैं जिनसे आप क्वेश्चन अच्छे से कर सकते हैं। सो यू कैन गो फॉर दीज सब्जेक्ट्स। गुड गुड ऋत्विक। आइए स्टिकियोमेट्री लिखते हैं। स्टिकियोमेट्री में बी डिफाइंड stoichiometry may be defined as a state for ionic compounds, as a state for ionic compounds wherein there is the exact ratio of cations to anions, wherein there is the exact ratio of cation to anion as predicted by chemical formula, as predicted by chemical formula, as predicted by chemical formula. For example, NaCl is stoichiometric. NaCl is stoichiometric if ratio of Na plus to Cl minus is 1:1. ठीक, ये इंजीनियरिंग सर्विसेज में पूछा गया. दिस हैज बीन आस्क्ड इन इंजीनियरिंग सर्विसेज. Do it quickly. Now, this stoichiometric defect can further be classified in two broad categories. This may be further classified in two broad categories. What are those categories? Have a look. The first one is Frankel's defect. Frankel's defect. And the second one is Schottky defect. The second one is Schottky defect. जरा Frankel's defect देखिए क्या है. Suppose you have ionic crystals. In the very beginning, I told you that cations are smaller in size than the anions. So, larger ions are anions and smaller one are cations. Let us suppose like this. So, they are arranged suppose like this. Larger one anions and smaller one cations. Suppose any cation is leaving its lattice position, ये अपनी position छोड़ देता है, and it occupies any interstitial position. It leaves its lattice position and occupies any interstitial position. Hence, this cation is creating two types of vacancies, vacancy here and interstitial defect here. So, a vacancy plus interstitial defect has been formed because of this cation. But overall charge is neutral because this charge is within the material, as well as ratio of cation to anion is also same because cation is within the material. So, overall ratio of cation to anion is not going to disturb, but this defect has been formed. So, it is a stoichiometric defect and such stoichiometric defects are known as Frankel's defect. Here you can debate ki why only cation is leaving its position, why not anion? Yes, theoretically anion may also leave its position and it may go to the interstitial position. But practically you see interstitial positions are very small spaces. So, cations are smaller in size, so there is a very high possibility that cation may fit into that interstitial position. Whereas anions are larger in the size, so their possibility of fitting into that small space is negligible. And this is the reason why I am saying that a cation is leaving its lattice site and reaching to the interstitial site. So, you can write it, a cation leaves its lattice site, creating a vacancy, and occupies an interstitial site, such kind of defect is known as Frankel's defect. A cation leaves its lattice site, creating a vacancy, and occupies an interstitial site. Such kind of defect is known as Frankel's defect. Here you see, again you have anion, cation, anion, cation, anion, cation, anion, cation, anion, cation, like this, anion, cation, like this, like this. Suppose a pair of ion is missing from the crystal, एक cation और एक anion. So if a pair of ion is missing from the crystal, vacancy defects are formed, but overall ratio will remain same. Earlier there were 100 and 100. Now what happens? 99, 99. Suppose a pair is missing. So you will have same ratio of cation to anion. It means stoichiometry is maintained, but vacancy defect has been found. Such vacancies where a pair of cation and anion is missing from the crystal, they are known as Schottky defect. So you can write a pair of cation and anion is missing from the crystal, leading to creation of vacancy defect. Such vacancy defects are known as Schottky defect. Such vacancy defects are known as Schottky defect. Please note down. Schottky defect has been asked recently. 1 or 2 years back it was asked. Done? Yes, Dharya. Next, non-stoichiometric defect. Non-stoichiometric metric defect. If a defect is formed such that the ratio of cation and anion is disturbed, it is not maintained as predicted by the chemical formula, then such defects are known as non-stoichiometric defect. Means either the number of cation is increased or it is decreased, then ratio will be disturbed, and then you can say that non-stoichiometric defect has been formed. ध्यान रहे, no matter what kind of defect is formed, crystal must be neutral. So first let us define non-stoichiometric defect, and then we would be talking about the types of non-stoichiometric defects. If there is any deviation, if there is any deviation from the exact ratio of cation to anion, from the exact ratio of cation to anion in the compound, then it is known as non-stoichiometric defect. Then it is known as non-stoichiometric defect. Non-stoichiometric defect. These are again of further two types. Now you see, my dear friend, let us suppose you have NaCl. So this cation is what? It is metal, and anion is what? It is non-metal. Anion is non-metal. So it is non-metal. So if ratio is disturbed, either the number of metals will increase or number of metals will decrease, or vice versa, number of non-metals will increase and number of non-metals will decrease. So you can have two types of defect. One, metal excess defect, where number of cations are increasing than the number of anions, and another, metal deficiency defect, where number of anions are increasing as comparison to the number of cations, right? So let us try to note it. First one is metal excess defect. Metal excess defect. When defect is formed number of cations become greater than number of anions. ठीक है, metal excess defect. Another one is metal deficiency defect. Metal deficiency defect. When defect is formed, number of cations become less than number of anions. ये as predicted by chemical formula के comparison में होगा, compared to प्रिडिक्शन बाय, वो समझ में आ रहा है, स्टिकियोमेट्री की डिफिनीशन में ही मैंने बता दिया. Now these metal excess defects are of two types further. The first type is, these are of two types. The first type is F center defect. Here an anion leaves its position and hence a vacancy is created. So let us suppose you were having 100 cation and 100 anion. So an anion is leaving position. So now you have 99 anion. So metal has become excess and a vacancy defect is formed in place of that anion. To maintain the charge neutrality, an electron is included in the vacancy. But electron is very small in the size. It can balance the negative charge, but it cannot balance the space. It cannot fill the space. So this way the crystal will remain neutral, but vacancy cannot be filled. फिर से सुन ले कि एक एनायन अपनी पोजीशन को छोड़ करके चला जा रहा है और उस जगह पर एक वैकेंसी क्रिएट हो जा रही है. एनायन के निकल जाने की वजह से कैटायंस की संख्या बढ़ गई, सो ये मेटल एक्सेस डिफेक्ट हुआ. जब एनायन निकल करके गया तो उस वैकेंसी में एक इलेक्ट्रॉन आ गया, तो इलेक्ट्रॉन ने एनायन का चार्ज तो बैलेंस कर दिया, मटेरियल पूरा न्यूट्रल रहा, लेकिन इलेक्ट्रॉन का साइज एनायन के साइज के कंपैरिजन में बहुत छोटा है, इसलिए एनायन के द्वारा जो जगह खाली की गई है उसको इलेक्ट्रॉन भर नहीं पाएगा और वैकेंसी डिफेक्ट क्रिएटेड रहेगा. सो यू कैन राइट इट लाइक दिस. An anion leaves its lattice site, creating a vacancy defect, and to maintain electrical neutrality, an electron is included into the vacancy. An electron is included into the vacancy. An anion leaves its lattice site, creating a vacancy defect, and to maintain electrical neutrality, an electron is included into the vacancy. The second one in this is interstitial ion and electron defect. Suppose an extra cation is included into the material at interstitial position. So number of cations will increase. Along with this cation, an extra electron is also coming into the material. So this electron will balance the extra positive charge of cation, material will remain neutral. But due to this cation, an interstitial defect is created. Such kind of interstitial ion electron defect is known as metal excess defect. An extra cation is occupying interstitial position, leading to creation of interstitial defect. To maintain electrical neutrality, an extra electron is also included. Extra electron is also included. An extra cation is occupying interstitial position, leading to creation of interstitial defect. To maintain electrical neutrality, an extra electron is also included. Quickly, इलेक्ट्रॉन लाने के बहुत तरीके हैं बेटा, किसी भी मटेरियल से खींच के ले आएंगे. Yes, Pratik, in case of Schottky defect, density will decrease. Now let us see metal deficiency defect. What happens here? A cation leaves its position, creating a vacancy, and the adjacent atoms acquire extra positive charge so that electrical neutrality remains maintained. Although this is very less frequent, still it can be formed. So लिखेंगे a cation leaves its interstitial its lattice position, creating a vacancy defect. A cation leaves its lattice position, creating a vacancy defect. To maintain electrical neutrality, adjacent atoms acquire extra positive charge. Please note down. मनोज, आपका क्वेश्चन नहीं समझ पा रहा हूं मैं. Is it done? Do it quickly. So this is all types of defect. Please, ये सारे तरह के डिफेक्ट हैं. हमने क्या कहा कि whenever there is change in order or periodicity of the crystal, then a defect is formed. जब भी एटॉमिक अरेंजमेंट में डिस्टर्बेंस होगा तो एक डिफेक्ट बन जाएगा. आइए जरा कुछ और बात करते हैं. एटॉमिक वाइब्रेशन. also known as lattice vibration. Both are same thing. Suppose these are the lattice points. These are the lattice points. And on each lattice point there is an atom. So it is perfect or ideal crystal structure. Each atom is at its lattice position. If we are at 0 Kelvin, then these atoms are exactly at the lattice point. But if we increase temperature, let us suppose we come to room temperature, then due to temperature there would be some thermal energy, and because of thermal energy these atoms start to vibrate around their mean position. So what happens? This atom starts to vibrate like this, above and down, above and down. When this atom is going at this position, so this lattice point is empty, and vacant atomic site is known as what? Defect, vacancy defect. Similarly, when this atom comes at this side, this becomes vacancy. So these atomic vibration, actual position is this. If atom is going this or this, this or this, so it means it is creating a kind of defect. So these atomic vibrations can also be thought of as a defect, can also be thought of as a defect. अखिलेश क्या पूछ रहे हैं आप? पिछला डिफेक्ट की अगर आप बात पूछ रहे हैं तो मैं क्या कह रहा हूं कि कोई एक कैटायन अपनी पोजीशन से छोड़ करके चला गया, तो जब कैटायन गया तो कुछ पॉजिटिव चार्ज चला गया, तो जितना पॉजिटिव चार्ज गया हुआ है उतना पॉजिटिव चार्ज उसके पड़ोस में जो एटम्स थे वो एक्स्ट्रा एक्वायर कर लेंगे और इस तरह से ओवरऑल सिस्टम न्यूट्रल बना रहेगा. ठीक है, यही बोला हमने. यहाँ आइए. So these atomic vibrations can be thought of as a defect. In atomic vibrations को भी हम लोग defect कह सकते हैं. अब एक चीज, किसी एटम का डिफेक्ट इंडिविजुअल तो नहीं हो सकता है, उसका वाइब्रेशन इंडिविजुअल तो नहीं हो सकता. These atoms are connected with bond with each other. They are connected with the bonds, तभी solid बना है. So all of them has been connected with each other through chemical bond. They has been connected through each other through chemical bond. ये जितने भी हैं chemical bond की मदद से एक दूसरे से connected. अब होगा क्या कि let us suppose this atom and this atom and this atom, they are connected through bond. So when this is going up, so this will go down, because bond means like this. So if goes up, then it goes down. When this goes down, this should go up. This way their vibrations are coordinated with each other. So a traveling lattice wave would be formed in the material. This lattice wave, which is formed into the material due to atomic vibration, this will help us to transport heat from one end of the material to the other end. For example, at this point I increase the temperature, so atomic vibration will increase. Because of the vibration of these atoms, neighboring atoms will also start vibrate. When it goes up, it goes down. So some part of energy is transmitted to the neighboring atom. Neighboring atom transmit to the next atom, and this way heat is being transported from one side of the material to the other side. So these atomic vibrations can be used to transport heat energy from one end of the material to the other end. When I was teaching you Bohr's model, I give you a very beautiful concept. When the particle is bound, its energy is quantized, E1, E2, E3, like that. But when particle becomes free, its energy becomes positive and continuous. Here the particle which is producing this heat energy, that is atoms, and atoms are bound, so their energy must be quantized. Their energy cannot be continuous. So this wave which is developed, this is basically a quantum of energy, a series of discrete quantum of energy. So one small quantum of this energy, this heat energy is quantized like this. So one small quantum of heat energy is known as phonon. ध्यान रहे, फोटान नहीं, फोनान. दिस इज वेरी ब्यूटीफुल थ्योरी. इंडिया के एक बड़े अच्छे साइंटिस्ट हुए हैं एस.एन. बोस, उन्होंने आइंस्टीन जी के साथ मिल करके बोस आइंस्टीन थ्योरी, एक बहुत शानदार थ्योरी दी हुई है जो इन पार्टिकल्स की बात करती है, और जहाँ से निकल करके आजकल जो एक बड़ा ही हॉट टॉपिक है गॉड पार्टिकल, उसकी थ्योरी निकल करके आती है. खैर वो सब पढ़ने का यहाँ समय नहीं है, स्कोप भी नहीं है, लेकिन एक दो लाइनों में जो चीज़ बताया हूँ इसको लिख लेते हैं. Yes, Pratik, you can say that, but that is possible only if there are molecules. Here we are talking about atomic solids, not molecules. Raghav Gupta, temperature is not zero. After sometimes it will come to its original position and then again it will go to other position. So this will keep on vibrating around its mean position. लगातार होता रहेगा, मीन पे आएगा. ये सिंपल हार्मोनिक मोशन फॉलो करते हैं, एसएचएम फॉलो करते हैं. लिखिए, एवरी एटम इन अ सॉलिड मटेरियल, मैं डिक्टेट कर रहा हूं, आपको लिखना होगा. एवरी एटम इन अ सॉलिड मटेरियल, every atom in a solid material is vibrating very rapidly is vibrating rapidly, yeah, very rapidly, is vibrating very rapidly about its lattice position. Every atom in solid material is vibrating very rapidly about its lattice position. About its lattice position. Full stop. In a sense, these atomic vibrations may be thought of as imperfections or defects. Imperfections or defects. Imperfections or defects. Full stop. Next point. These vibrations are coordinated. These vibrations are coordinated in such a way these vibrations are coordinated in such a way that traveling lattice waves are produced. Traveling lattice waves are produced. Traveling lattice waves are produced. Full stop. The thermal energy of these lattice waves, the thermal energy of these lattice waves, the thermal energy of these lattice waves is quantized, is quantized, is quantized. Quantized मतलब discrete, is quantized, and a single quantum of vibrational energy and a single quantum of vibrational energy is called as phonon. Is called as phonon. ठीक है जी. आइए, my dear friend, up till now you may have observed that all these defects are mainly of three types: vacancy, interstitial or substitutional. No matter whether it is Frankel, Frankel is nothing but interstitial plus vacancy, Schottky is nothing but vacancy, epicenter, that is. Also, someone asked you why the name is epicenter. I don't know why the name is epicenter. Frankly speaking, I have not found in any text why the name is given epicenter. Maybe some scientist's name, initial name like that. Maybe, I'm just guessing. I don't know why it has been named. Right, come to the point. So, vacancy, all these defects can be classified as three broad categories. They are vacancy, interstitial, या substitutional. Let us suppose this is our crystal structure. These are the atoms. So, this is our ideal crystal structure. Suppose you have a vacancy defect, means one or two atoms are missing from their lattice point. So, here a vacancy is found, or you have an interstitial defect like this, or you have a substitutional defect like this. These are the three broad categories of defect. Suppose you apply voltage and an electron starts to move from low to high potential like this. Right. If an ideal crystal, the electron is moving from low to high potential, but if it is a vacancy, then electron may get trapped into vacancy. So, its motion will stop here, or vacancy को you can consider like a discontinuity. You can हिंदी में बोले तो एक गड्ढे की तरह consider कर सकते हैं जहाँ पर इलेक्ट्रॉन गिर सकता है. So, either you will get trapped in this vacancy, so it will not be able to reach here, and if it is not able to reach here, it will not contribute into the current, or it may change its path, and when it is changing its path, it means it is getting scattered. Similarly, here if electron collides with this impurity, it may get scattered. Similarly, here because of unequal size, it may get scattered. What my conclusion is, कि any kind of defect in the material is trying to scatter the electron, and if electron is scattered, its contribution into the current will get finished, because current will flow when the net displacement of charge will take place, and net displacement of charge will take place only when the electron is reaching from low potential to high potential. But if there is a vacancy, there is interstitial defect, or there is substitutional defect, it is scattering the electron. And this scattering is resulting into decrease in conductivity या increase in resistivity of the material. So I can say that अभी resistivity conductivity की बात नहीं करते हैं. Let's stop it here. Just we can conclude one point from this all discussion that कि whenever there is a defect into the material, that defect will try to scatter the electron. वो defect किसी भी कारण से आया हो, no matter with what reason this defect has been formed, but if there is a defect into the material, this defect will try to scatter the electron. So any kind of crystalline defect, any kind of crystalline defect will function as a scattering point for the movement of electron. Any kind of crystalline defect will function as a scattering point for the movement of electrons. Means if there is any defect, it will try to scatter. Please note down this point. I would be using it in the later sections of our discussion. Maybe बेटा धैर्य, I do not recall. हो सकता है फार्ब मीनिंग हो. No, it's not new chapter, Pratik. Just I am going to start the new chapter. Nishtha, you are answering your question itself as there is no atom. So electron will not go to that vacancy. Electron will try to love to move from atom to atom. So it will take the atom of other side, right? So your question is giving answer. आपका प्रश्न ही आपका आंसर दे रहा है. Electron loves to move from one atom to another atom, and in the vacancy since there is no atom, so it will take the neighboring atoms of other side, and hence its direction is changed, means it is getting scattered. कई बार हमारी प्रश्न ही जवाब होते हैं. आगे बढ़ा जाए. Can we proceed? किसी ने कहा कि सर प्लीज प्रोवाइड योर फोन नंबर. डियर, सिंस आई टीच इन ऑल द ब्रांचेस and every year lots of students study in my classes, and also I am teaching 5 subjects. So this is the only one subject in the GS, remaining 4 are the technical subjects. So I am teaching 5 subjects. It means every year I am going to a large number of students. So if I share my number, then my mobile will become a call center. So you can understand that it's not practically possible to pick call of every student, and that is the reason I have given you Telegram ID. Contact me at Telegram. I will definitely try to reach you. I will definitely try to solve your query. Once you get selected in any stage, let us suppose you qualify prelims, you come to mains, or you go for the interview stage, then I share my number, because then less number of students are there and it is easily able to be manageable. So once you qualify 1 or 2 stage of the examination, then if you contact, I will be sharing my number. My number is with so many students. but in the larger crowd, because of this practical reason, I am not able to share the number, because everyone will be trying to call and it will not be possible to pick the call. So that is no meaning of sharing the number. चलिए आगे बढ़ते हैं. सो इति श्री द्वितीय अध्याय समाप्ति मापनोत. बोलो सत्यनारायण स्वामी की जय. We have finished chapter 2 and we are moving towards chapter 3. Chapter 3 is electric properties of materials. Electric properties of materials. Means we would be giving some electrical excitation. Obviously that excitation is in the form of voltage, and we are wanting to see the behavior of material under that electrical excitation. Voltage means EMF, electromotive force, जो electron को motivate कर सके कि भाई तू दौड़ जा. So if electron is able to move under the influence of a voltage, then the material is known as conductor. And if it is not able to move under the influence of a voltage, then the material is known as insulator. So in this chapter, we have to investigate the property of the material with respect to the applied electrical force. The behavior of the material under the influence of mechanical force is quite different than the behavior of material under the influence of electrical force. Mechanical forces we can feel, we can experience in day-to-day activity. बचपन से आपने किसी को थप्पड़ मारा, so it was a mechanical force. What was the response you have observed? So you have done lots of experiments since your childhood regarding the mechanical forces. And that is the reason why mechanical properties are easily understandable. And easily your brain is able to correlate with the mechanical behavior of the material. But electrical phenomena happens at the atomic level. Electron none of us had seen up till now. So correlating with the behavior of electron sometimes becomes very difficult for us. An electron is very small particle, very tiny particle. So a tiny particle may not behave like the large objects. It may behave in a different way. So sometimes our intuition is not going to help you in understanding this property, because we have not seen the things experimentally since our childhood. Here we have to believe what the mathematics is saying. We have to believe what the standard assumptions has been saying. Here our intuition may give wrong result. So I am giving you this caution before you start this topic. Don't try to judge things based upon your intuition. Intuition becomes correct when you have seen lots of such kind of circumstances in your life. So that is actually different experiments through which you have gone in your life, and on the basis of those experiments you are giving certain conclusion, and that conclusion goes to correct direction. But here, since you have not seen the electron, you have not done the experiments in your life regarding this, so your intuition may not give good result. ये मेरा अपना इलाका है, electric properties, and मेरा अपना इलाका से मतलब I have done my engineering in electronics and communication engineering. So 4 years of degree and 12 years of teaching, 16 years I have invested in this area. And I have done a job also in the field of communication engineering. I was with the government of India in Prasar Bharati. You may have heard the name of Prasar Bharati, that is Doordarshan. So this whole field of electrical engineering fascinates me. This whole field of electrical and electronics engineering fascinates me. So you are most welcome to ask any kind of query in your mind whenever I am teaching. I will try my 100% to rectify that query, except one request, and that is related with the language, right? Apart from the request related with the language, I will be trying to take each and every query of yours. Most of the electrical materials which we are interested to study, they are the solid materials. So let us start studying the solid. My dear friend, here we have to study the motion of electron. Motion of electron, so our object is what? Electron. Some force would be applied on the electron, and how this electron is moving, that we have to study in this chapter. Electron is moving, it means it has some energy. Any object will be able to move only if it had some energy. So we are wanting to investigate how much energy this electron is having, because if we will have idea about the energy of electron, then we can conclude that how this electron would be moving into the material. So let us have an idea how this electron is moving, but before that let us try to investigate how much energy this electron is having. That energy will quantify कि how it can move. क्योंकि हम सभी जानते हैं कि अगर किसी पार्टिकल के पास एनर्जी होगी, फॉर एग्जाम्पल आई एम मूविंग हियर, so how I am able to move? Because I am having some energy. I have taken a tea, that tea has given me some energy, and because of that energy I am able to move here. So if you are wanting to see my movement, then first you should see how much energy I am having, and that energy will tell you how much time, for what duration I can be able to move, and when I will collapse due to lack of energy. So we are first of all wanting to investigate about the energy of electron. My dear friend, up till now we have seen that the energy of electron depends upon several factors. For example, suppose we have one atom, this is the atom, and this is the nucleus. So this nucleus is attracting this electron, and because of this attraction force, this electron is having some amount of energy, and in an atom this energy of electron be plotted like this, energy of electron. How does we plotted it? If you recall, it is E1 first energy level, then E2 second energy level, and then likewise E3 up to so on. So the energy of electron in an atom, when plotted on the graph, it gives us discrete lines. So each line represents a level, a position of energy. So this diagram is known as energy level diagram. My friends from electrical engineering and from electronics engineering, अच्छा इलेक्ट्रॉनिक्स वाले वो लोग जिन्होंने मुझसे ईडीसी पढ़ी होगी वो थोड़ा बोर होंगे कुछ देर के लिए, बैठे रहो चुप्पे, रिवाइज कर लो, ठीक है। और जो इलेक्ट्रिकल वाले हैं बैठो, कुछ नए वे में चीज़ें देखेंगे। बेटा ये जो दो चैप्टर अगले हैं ये आपकी टेक्निकल मटेरियल साइंस के सिलेबस का भी पार्ट हैं, तो मैं ही आपको टेक्निकल मटेरियल साइंस भी पढ़ाऊंगा, लेकिन जो यहां पढ़ा चुका रहूंगा वो दोबारा वहां पर नहीं पढ़ाऊंगा, तो आप छोड़ नहीं सकते हैं इसे, ठीक है। यहां के आगे वहां पर कंटिन्यू करूंगा, इसी हिसाब से मेडी जी ने मुझे टाइम दिया है। What I said, I am repeating it in English. The students who are from electrical and electronics branch, the next two chapters, this chapter and the next chapter, they are the part of your technical material science syllabus as well. The technical material science syllabus will be taught by me, and there I will start teaching here onwards. I will skip all those things which I am teaching here, and the things above this level, those which are not taught in the syllabus of basics of material science, those will be taught in the syllabus of technical material science. So both of these will complement each other. This which we are teaching, reading in the basics of material science, and plus something extra would be required for the technical material science. The study which we are doing here, that will not be sufficient to do all the questions of the technical material science. To do the questions of paper 2 material science, you need a further class of approximately 25 hours that I would be taking separately. Management may be planning after this class or sometime after that to that 25 hours of the class. So that 25 hours of the class will cover basics of will cover material science, especially from electrical and electronics engineering point of view, and that will comprise the paper 2 syllabus. But what we have been discussing here, that will also be used to study the further topics, so you cannot skip it. And electrical people, please never try to ignore ignore this subject. Your selection is guaranteed by this subject, because if you see last 2-3 years paper, material science, which you study 30 hours here in basic material science and 25 hours in technical. So in total you study 55 hours. This 55 hours is giving you more than 25 questions, 14 questions roughly in paper 2, 14 to 15 questions, and 10 to 12 questions if I take in paper 1. So roughly 25 to 30 questions you are going to get from material science paper 1 and 2. Any other subject is not having this much of huge weightage for the electrical engineers. So if anyone is from electrical engineering branch and he is trying to skip material science, it means he is planning to come next year to MEDIG to study the material science. मेरे लिए तो अच्छा है, आप 2 बार पैसा देंगे, इस बार भी और अगली बार भी, लेकिन आपका 1 साल और तमाम सारा पैसा बर्बाद जाएगा अगर आप इस सब्जेक्ट को ठीक से नहीं पढ़ रहे हैं। बाकी ब्रांचेज के लिए जीएस के पॉइंट ऑफ व्यू से आइए। So I said that this is energy label diagram, where each label is representing energy of the electron in the various orbits when we are talking about electron in an atom. I told you the molecular orbital theory. I said that when 2 atoms come closer to each other, these are the 2 atoms and they are coming closer to each other. So these atoms start attracting and repelling each other. Because of this, I told you, if I plot the energy of these 2 atoms, so when they are individual atoms, their energy will be same. Electron will have same amount of energy. बड़ा basic से पकड़ूंगा, and this is the reason why I invested 5 lectures in chapter 1 and 2. Once chapter 1 and 2 are clear, then all the chapters are very easy to understand, because all the chapters are the application of these first 2 chapters. Then I said that due to attraction force, energy will start decreasing and at certain point it will become constant, and due to repulsion force, energy will start increasing and at certain point it will become constant. My dear friend, if I plot this molecule's energy, then I can plot it. इसी वालों, तुम ये सोचते चलो कि एज अ टीचर मेरी कितनी नैतिक मजबूरियां हैं कि बिना श्रोडिंगर इक्वेशन की बात किए हुए, बिना क्वांटम फिजिक्स की बात किए हुए और बैंड डायग्राम समझाना है, वो भी सिविल और मैकेनिकल के बच्चे को, उसमें से भी आधे जो मुझसे नाराज बैठे हुए हैं, गुस्से में बैठे हुए हैं, मैनेजमेंट के डिसीजन की वजह से वो टीचर को विलन मान करके बैठे हुए हैं, और वहाँ पर मुझे समझाना है, कितना डिफिकल्ट होगा मेरे लिए। तो तुम लोग सहयोग करते रहिएगा, अपने फ्रेंड्स को समझाते रहिएगा, क्योंकि तुम्हें तो इसमें मास्टर बना दिया हूँ अगर मुझसे पढ़ चुके हो तो। आइए फिर भी रिवाइज करते चलें। तो आप एक चीज देखें कि जब दोनों एटम एक दूसरे से बहुत दूरी पर हैं, try to understand when both of these atoms are far away from each other. So they are the isolated atoms and the energy of electron is exactly same. So if I plot energy of electron in molecule, energy of electron in molecule, if I am plotting this, then what happens? Initially when, and this axis I am taking interatomic spacing. Interatomic spacing means distance between the 2 atoms, right? So when these 2 atoms are far away from each other, the energy of electrons is same. So let us plot it like this. This is the energy and that energy is same. I am making a graph. So all these atoms are having same energy when they are far away. But as they come closer to each other, the energy is split into the 2 different energy levels. Because these atoms start interacting with each other, they start applying attraction and repulsion force, and because of this force, their energy get split. Because of attraction it goes to downward and because of repulsion it goes to upward. So this energy level is split into 2 different energy levels. Right? One is sigma and other is sigma star. Sigma is representing bonding molecular orbital energy and sigma star is representing anti-bonding molecular orbital energy. If you recall, I told you that for a stable structure, number of electrons in bonding molecular orbital must always be greater than number of electrons in anti-bonding molecular orbital. Let us redefine it. For a stable structure, number of electrons in lower energy states must always be greater than the number of electrons in higher energy states. Do you agree with this? Because the same thing I told you, for a stable bonding, number of electrons in bonding molecular orbital must always be greater than number of electrons in anti-bonding molecular orbital. It means here in the lower energy state, this represents bonding and this represents anti-bonding. So here the number of electrons must always be greater than the number of electrons here, right? One more important observation: when there was a single atom, energy was represented in terms of discrete energy levels. When two atoms are coming closer to each other, then energy is split in two different energy levels. For the same electron, energy will have certain difference. Still you have two energy level, so still it will be known as energy level diagram. अभी भी इसे हम लोग एनर्जी लेवल डायग्राम कहेंगे. एनर्जी लेवल डायग्राम for the energy of electron in a molecule, for the energy of electron in a molecule. Now let us start building the crystal. Crystal cannot be made by two atoms. Large number of atoms will come into the close proximity to make the crystal. So let's take a hypothetical condition. Suppose n identical atoms are coming closer to make the crystal. And it's not hypothetical, it's actually practical. If you recall, in a mole, Avogadro number के बराबर atoms होते हैं. A mole of substance is containing number of atoms equal to Avogadro number. What is the Avogadro number? That is 6 into 10 to the power 23 atoms. So such a large number of atoms are coming closer to each other to make the solid. When these large number of atoms will come closer to each other, they will start interacting with each other. So they will start attracting and repelling each other. So energy of electrons will change. So let us try to plot that energy of electron when n identical atoms are coming closer to make the solid. So next point is, let us assume that n identical atoms are coming closer to make solid. N identical atoms are coming closer to make solid. Let us suppose n identical atoms are coming closer to make solid, right? Let's plot their energy. When these n atoms will come closer to each other, so they will start interacting with each other. So here on the graph, this is energy of electron, and here we have interatomic spacing. Interatomic spacing means distance between two atoms. Initially we are assuming that all these atoms are far away, they are at infinite distance, so they are not attracting or repelling each other. So each electron will have same energy, like this. Here when the atoms are far away, the energy is same, like this and this, both energies are same. So when atoms are far away, the energy will be same. Now when we start decreasing the distance between these atoms, हम इनको close लाना start कर रहे हैं. We start decreasing the distance between the atoms. They will start interacting with each other. When atoms start interacting with each other, their energy levels split. So which was single energy level, it converted into two different energy level. When there were two atoms. But now how many atoms are there? Now there are n atoms. So energy level will split into n different energy levels. If there were two energy levels, two atoms, energy was split in two levels. If there are n atoms, then our intuition will definitely say that energy is split into n different levels. So this energy is going to split into n different energy levels. So it is splitting into n energy levels. N energy. These n energy levels are very closely spaced with each other. वो आपको समझाने के लिए मैंने इतना गैप दिखा दिया है दो लेवल के बीच में. Although the gap between two level is negligible, so we can have a range of energy. This is a range of energy. Range of energy. This range of energy is known as energy band. This range of energy is known as energy band. What I am wanting to tell you कि energy of electron in an atom or in a molecule can be represented by discrete energy labels, but energy of electron in a solid need to be represented by a range of energy, and this range of energy is known as energy band. Right? So let us try to note down this point. Hence, energy of electron, energy of electron, energy of electron in an atom or molecule can be represented by discrete energy labels. Discrete energy labels. But energy of electron in a solid need to be represented by a series of energy levels, represented by a series of energy levels, a series of energy levels. These energy levels are very closely spaced. These energy levels are very closely spaced, and hence they are forming a band of energy, hence they are forming a band of energy. तो इसको आप पूरा इस तरह से डिस्क्रीट लाइन लिखने की बजाय आप इस पूरे बैंड को ही इसके लिए रिप्रेजेंट कर सकते हो. यू कैन रिप्रेजेंट लाइक दिस. दिस होल बैंड इज energy of electron, like this band. This is representing energy of electron when solid is formed. Up to this point, solid is not formed. Solid is formed when the interatomic spacing has become stable. So that has become stable at this point. So this way, this series of energy levels is known as energy bands. So biggest point which we need to conclude here is that energy of electron in an atom or molecule can be represented by discrete energy levels, but energy of electron in the solid cannot be represented by discrete energy level. Instead, it need to be represented by the energy band, series of energy levels which are very closely spaced. So this series of energy level which is very closely spaced is known as energy band. Please इसमें जो कुछ भी आपको लिखना या लिखने का मन करे वो लिख डालिए. From here we started. Quickly note it down, whatever you are wanting to note down, and then we would be moving next. Yes, जहां से एनर्जी स्प्लिट हुआ, जहां पर स्टेबल हुआ है, दैट इज इक्विलिब्रियम इंटरएटॉमिक स्पेसिंग. प्रतीक, बॉन्ड कब बनता है? जब स्टेबल हो जाती है एनर्जी, कांस्टेंट हुई. जहां से स्प्लिट हुआ वहां से इट स्टार्टेड टू चेंज, अट्रैक्शन और रिपल्सन लगना स्टार्ट हुआ. जल्दी करें। जी जी रोहन, हम इंडिविजुअल ऑर्बिट की ही एनर्जी को स्प्लिट कर रहे हैं। जी हां, अगर इलेक्ट्रॉन हाई एनर्जी स्टेट में गया ओंकार, देन इट विल बिकम अनस्टेबल। तो वो देखेंगे कि वो कहां जाएगा। ऑब्वियसली हमेशा क्या होना चाहिए, हाई स्टेट में कम और लो स्टेट में ज्यादा। Yes, molecular orbital theory is applicable. Actually, I am taking the help of molecular orbital theory to explain the splitting of the energy level, not in exact sense. उसके बाकी की चीजें हम लोग नहीं कंसीडर कर रहे हैं। No, if equal distribution of electron in bonding and anti, acha, you are saying energy, Mukul Sachdeva, sir, we can say that there is equal distribution of energy bonding and anti-bonding. That I would be discussing, yes. अखिलेश, हमने पीछे एक्सप्लेन किया है जहां मॉलिक्यूलर ऑर्बिटल थ्योरी पढ़ा है, रिपल्सन में इलेक्ट्रॉन्स इज गोइंग अवे फ्रॉम द न्यूक्लियस एंड ग्रेटर द डिस्टेंस ऑफ इलेक्ट्रॉन फ्रॉम द न्यूक्लियस हायर इज इट्स एनर्जी। भूल गए? ऐसे भूलोगे तो फिर कैसे काम चलेगा? प्लीज कीप ऑन रिवाइजिंग द थिंग्स व्हिच वी डिस्कस्ड इन चैप्टर 1 and 2, they will be utilized. Yes, Raghav, that I have told so many times कि for stable bonding, number of electrons in the bonding molecular orbital, it means lower energy state must always be greater than number of electrons in the anti-bonding orbital. Is it done? Can I continue? कल तबीयत ख़राब थी तो थोड़ा सा रेस्ट करने का भी मौका मिल गया एक बिजी शेड्यूल से, और थोड़ा सा मूड भी शांत हो गया। Otherwise, I was feeling a bit sandwiched between management and students' expectations. Shall we go ahead? क्या आगे बढ़ा जाए? अच्छा, क्लोजली स्पेस्ड लिखना भूल गया है, कहीं मैं भूल गया हूं। Hence, energy of electron in an atom or molecule can be represented by discrete energy levels, but energy of electron in a solid need to be represented by a series of energy levels. These energy levels are very closely spaced I forgot to write here closely spaced. Means distance between two levels is negligible and hence they are forming a band of energy. Closely spaced. आगे चले. Now put heading. Energy bands in solids. I am taking the example of silicon and trying to explain the concept of energy band. That is equally valid for the other solids also. I am taking the example of silicon because silicon is very important. In this chapter, 9 questions has been asked in past 6 years. And out of 9 questions, 4 or 5 I think, I forget, I think 5 questions are related directly or indirectly from silicon. So silicon is very important material. So I am taking the example of silicon, although the theory is valid for the other solids also. बड़ा अच्छा कोट लिखा है मनोज जी आपने. The less we stop at the small stations, the sooner we reach the big junction. Good. Consider a silicon atom. Consider a silicon atom. Let's consider it. Silicon has atomic number 14. So if I do electronic configuration, it is 1s2, 2s2, 2p6, 3s2, 3p2. My dear friend, if you recall, I am never interested in the inner orbit electron. All the material properties will be defined by the outermost orbit electron, barring few exceptions. कुछ exception को छोड़ दें तो हमेशा. So these are core electrons. We are not interested in these core electrons. They do not participate in bonding. In bonding, these electrons participate. These are known as valence electrons. So silicon has 4 valence electrons. So I would be talking about these 4 valence electrons. It means 3s and 3p are the valence orbits. Here I am taking one assumption. I am assuming that at each state there can be 1 electron. वैसे हमने आपको बताया था कि there can be 2, एक anti clockwise and clockwise. Separate them also, consider them as 2 different states. So let us, it is one state and it is another state. So I am assuming that at each state there can be only 1 electron. ठीक? Here we are assuming that at each state there can be only 1 electron. Only 1 electron. There can be only 1 electron. At each state there can be only 1 electron. ठीक है जी, आइए जरा देखते हैं. So in this silicon atom, मुझे थोड़ा ध्यान से सुनते चलें. In this silicon atom, forget about the inner one. We have 3s state. So this 3s has 3s orbital basically. So this 3s has 2 states. At max, how many electrons can be? 2 electrons can be. ठीक? And 3p. So 3p at max, how many electrons can be? There 6 states. So it is 6 states, right? So we are having total 6 plus 2, that is 8 states. Total 8 states. Out of 8 states, how many electrons are there? 2 plus 2, 4 electrons. So in each atom, out of 8 states, 4 states are occupied by electrons. 4 states are occupied by electrons, occupied by electrons, and 4 states are empty. 4 states are empty of electron, empty of electron. So there are total 8 states, 2 in the S and 6 in the P. P में कितने electron maximum possible? How many maximum electrons are possible in P? 6. So each electron is considered as a state. So there can be maximum 6 states in the P and 2 in the S. So there is total 8 states. But in the silicon, how many electrons are there? 4 valence electrons. So out of these 8 states, 4 are filled by the electrons and 4 are empty. पहले आप यहाँ तक लिख लें, फिर उसके आगे मैं कुछ बात करता हूँ. First you write here. किसी ने पूछा सर आप आईएएस थे? नहीं, एक्चुअली मैं जब फाइनल ईयर में ही था, यूपीएससी कई सारे सेपरेट एग्ज़ाम भी करती है, तो ऐसा ही एक एग्ज़ाम उन्होंने कंडक्ट किया था ग्रुप ए गस्टेड ऑफिसर की ही पोस्ट के लिए, विच इज़ इक्विवेलेंट टू आईएएस पोस्ट. पहले सेंट्रल गवर्नमेंट में बहुत वैकेंसीज निकलती थी ड्यूरिंग मनमोहन सिंह टेन्यूर व्हेन कांग्रेस वाज इन. सो ग्रुप ए ऑफिसर की पोस्ट थी मिनिस्ट्री ऑफ इंफॉर्मेशन एंड ब्रॉडकास्टिंग, जिसके अंतर्गत में हमारा ये कम्युनिकेशन से रिलेटेड सारी चीज़ें आती. So I appeared in this examination. There were roughly around 6 or 10 seats. I do not exactly remember. I think 10 seats were there and 6 for general, like that was there. So I qualified this examination of UPSC and then got selected in Ministry of Information and Broadcasting and was posted in Delhi in Prasar Bharati as Assistant Executive Engineer. So it is my profile. Later on I got selected at several places. But those who were advising me, like B. Singh sir and all those persons, they said that instead of running behind engineering services, since you are at the same place now, you should start preparing for civil services. So I'm 2010 pass out, and in 2010 I got this job. Then I start appearing for civil services. To 2011. First time appeared in the civil services and I reached up to the interview, but unluckily was not qualified. So then given next 3 attempts more I have given, and out of those 3 more attempts, so first is this and 3 more, so total 4 attempts I appeared. So 3 times I appeared into the interview out of these 4 in the civil services, but unluckily could not qualify. And since I could not qualify civil services, इसीलिए आज आपको पढ़ा रहा हूँ. So वो नहीं निकल पाया, तो उसके बाद फिर जीवन को जो मंजूर था, then I was having choice कि whether I should be in the job related with this engineering field. It was a core job, good job, there was good money also, or I should go for the teaching. Here the money was more than the central government in the in this coaching industry. So in 2014 I take a call कि I have done BTech to earn more money. So I started to teach with Mediji and resigned from the job. This is brief journey about me, not more than that. Although I have been selected in several other organizations also. I have given total 22 interviews, including these 3 also. So out of the 22 interviews, I qualified 4 and 18 times I failed. So I have more failure story than the success story. So out of 22 interviews, I qualified in 4 interviews. So finally was selected in 4 organizations and rejected in 18 organizations. So this is the success story or failure story, what you can assume. Let us come back to this point. Please. 4 states are occupied by the electrons and 4 states are empty of electron. Let's go. I took optional as electrical engineering because electronics engineering is not in the syllabus of UPSC. So I took electrical engineering. Electrical engineering was my option. Please come back. Let us consider n such atoms are coming closer to make solid. So if n such atoms are coming closer to make solid, then in silicon crystal, silicon solid, whatever you are wanting to say, how many states would be there? In a single atom there are 8 states. So if n atoms are coming closer, so there would be 8n states. So here we are having 8n states. For one atom 8 states, so n atoms 8n states. For one atom there are 4 electrons. So for n atoms there would be how many? 4n electrons. So 4n states are occupied by the electrons, and 4n states are empty of electrons. 4n states are occupied by the electrons and 4n states are empty of electrons. Agreed? Now my dear friends, if you have 2 states, then they split in bonding and anti-bonding. So if you have 8 states, then 4 will become bonding and 4 will become anti-bonding, right? So if you have 8n states, then 4n will become bonding and 4n will become anti-bonding. So if I want to draw the band diagram, then I will have like this. Energy of electron, and interatomic spacing. Rather directly leave it. Unnecessarily don't make it complex. So out of these 8n states, 4 will become bonding states. So these are the 4n states, they are the bonding states. So let us assume that these are the 4n states. And there should be a gap between bonding and anti-bonding, and after this gap there will be further 4n states. So these are the again 4n states. So these 4n states will become anti-bonding states. And this would be the gap between these states. जैसे आपके पास ऐसे होता है, like this. If one state, so it is sigma star, it is sigma, and this is the gap. So these are the 4n sigma star, and these are the 4n sigma, and this is the gap. This way the things are going to happen. How many electrons are there? You have 4n electrons. So all these 4n electrons will be occupying these positions. They are occupying these positions. You have only 4n electrons. So these 4n states, are occupied by valence electrons. Since these states are occupying valence electrons, so this range of energy, this band of energy is known as valence band. Since these states are containing valence electrons, so this band of energy is known as valence band. This band of energy is known as valence band. In short, I would be writing as. Now, these 4n states are empty of electrons. Let us suppose we are at 0 Kelvin, no external energy is given. These states are empty of electrons. States are empty of electrons. Empty of electrons. This band of energy is known as conduction band. This band of energy is known as conduction band. Q, the reason would be obvious very soon. The difference between these two energy range, electron is allowed to stay either in this band or in this band. It cannot allowed to stay in this range. So this is known as forbidden energy band gap. Forbidden energy band gap. Forbidden energy band gap. This is known as forbidden energy band gap. Electron is not allowed to stay in this gap. Electron is not allowed to stay in this gap. Not allowed to stay in this gap. Stay in this gap. It can be either in valence band or in the conduction band, but it cannot be in the forbidden band gap. You please note down this, then I have to tell something here. Please note it down. बेटा वो हमने एक ही एनर्जी लेवल लेकर के दिखाया था, सिर्फ बॉन्डिंग वाले दिखाए थे, बैंड कैसे बन रहा रमन, ठीक है। अब जब हम पूरा डिटेल में देख रहे हैं तो हम सिर्फ बैंड बनाना नहीं बता रहे हैं, टोटल कैसे बॉन्डिंग एंटी बॉन्डिंग है दोनों दिखा रहे हैं। वहां भी आप दिखा सकते हैं गैप को। अभिषेक कह रहे हैं कि सर आई डू हैव अ क्वेश्चन, व्हाई डू आईएएस रिजाइन इजीली एंड परस्यू अ डिफरेंट करियर बट एन आईएएस रिजाइनिंग रेयरली। नहीं, यू हैव रॉन्ग अजम्पशन। नीदर आईएएस रिजाइन इजीली नॉर आईएएस रिजाइन इजीली। ना ही आईएएस आसानी से छोड़ते हैं और ना ही आईएएस आसानी से छोड़ते हैं। वो क्या है कि तुम मेडिजी में हो तो यहां तमाम सारे लोग आ गए हैं तो तुम्हें लग रहा है कि आईएएस बड़ी आसानी से छोड़ देते हैं। नहीं, कितने लोग हैं यहाँ? हार्डली 30, 35, 40, वो भी 20 साल में, ठीक है। तो 40 लोगों ने 20 साल में छोड़ा हुआ है। इतना अगर आप आईएएस देखोगे, क्योंकि आप उस फील्ड में नहीं हो तो इसलिए आपको नहीं पता, इतने वहां भी छोड़े होंगे। बाकी बहुत कम लोग आईएएस छोड़ते हैं, बहुत कम लोग आईएएस छोड़ते हैं। बड़ी ड्रीम जॉब्स हैं, बड़ी नौकरियां हैं। जनरली जो लोग छोड़े हुए हैं, चाहे वो इंजीनियरिंग सर्विसेज छोड़े हुए हैं या सिविल सर्विसेज छोड़े हुए हैं या कोई अन्य गवर्नमेंट जॉब छोड़े हुए हैं, कोई भी ग्रुप ए गजेटेड ऑफिसर की पोस्ट तभी छोड़ता है जब उससे बेहतर कोई ऑप्शन उसको दिखाई देता है, अन्यथा नहीं छोड़ता है, ठीक। सो ये आपका एजम्पशन रॉन्ग है। डियर अपूर्व, मैंने आपको बताया था कि बोहर ने क्या कहा कि इलेक्ट्रॉन विल बी ओनली एट दोज प्लेसेस वेयर MBR इज इक्वल टू NH/2π। तो जब मैं मॉलिक्यूलर ऑर्बिटल थ्योरी पढ़ा रहा था तो आपने देखा होगा कि एनर्जी लो होती है और हाई होती है और दोनों के बीच में कुछ गैप रहता है, ठीक। ये वही गैप है कि इलेक्ट्रॉन या तो लोअर एनर्जी स्टेट पर अट्रैक्शन फोर्स के कारण है या अपर एनर्जी स्टेट पर रिपल्सन के कारण है। बीच की किसी स्टेट पर वो नहीं रह सकता क्योंकि बीच की किसी भी स्टेट पर उसका एंगुलर मोमेंटम इंटीग्रल मल्टीपल नहीं होगा। जी प्रतीक, यहां हर एक स्पिन के लिए भी हमने एक सेपरेट एनर्जी स्टेट माना है। अर्पित पूछ रहे हैं सर आप रहने वाले कहाँ के? मैं यूपी का रहने वाला हूं, उत्तर प्रदेश से। जुगुंसी इज कहें सर कंग्रेचुलेशंस ऑन योर सक्सेस फॉर सम टाइम, इट्स अ ड्रीम इवेंट टू पास प्रीलिम्स एंड थैंक यू फॉर गेट। नो इट्स नॉट लाइक, मतलब ऐसा नहीं है कि मुझे कोई रेग्रेट है या कुछ ऐसा है कि जिसकी वजह से मुझे ऐसा लग रहा हो कि नहीं हुआ तो गलत हुआ, नहीं। डेस्टिनी में हैव डिसाइडेड समथिंग बेटर देन दैट, इसीलिए उन दिनों नहीं हुआ। तो अभी ऐसा कुछ नहीं है लाइफ में कि कुछ रेग्रेट करने को है। लाइफ हैज़ बीन वेरी बेनोवेलेंट एंड इट हैज़ गिवन ट्रमेंडस सक्सेस। मेरी अपनी एक फेमस सेइंग है, कई बार जब वैसे मैं ऑनलाइन प्लेटफॉर्म्स पर तो कम जाता हूँ, लेकिन कॉलेजेस वगैरह में बहुत जाता हूँ। मैंने भारत के लगभग 300 to 400 कॉलेजेस या उससे भी ज़्यादा में 500 के आसपास कॉलेजेस में लेक्चर्स या सेमिनार्स लिए होंगे। कई बार मोटिवेशनल, कई बार सब्जेक्ट से रिलेटेड लेक्चर्स। तो वहाँ मैं एक बात कहता हूँ कि सक्सेस इस बात से नहीं मापी जानी चाहिए कि आप आज कहाँ खड़े हैं, बल्कि सक्सेस इस बात से मापी जानी चाहिए कि आपने सफ़र कहाँ से शुरू किया था और आज कहाँ खड़े हैं। In my opinion, success should not be measured from this point कि where do you stand today. Instead, it should be measured in terms कि from where you started the journey and where you stand today. So in my opinion, from where I started journey and today where I am, it is a tremendous success, and God has been very benevolent on me. He has shown me the path and He has given me opportunity to grow myself. I am the only son of my parents and I have 5 elder sisters. 4 of my elder sisters have not been to the school. They are illiterate. One who is just elder to me, she is she has studied only up to the 5th class. So my all siblings were of the same caliber what I am. But at that time there was no school, the things were, the village is very remote and there were not facilities. So they did not get opportunity to learn. But it was God's decision when I was very young, then nearby to my village a primary school opened and I got opportunity to learn at very young stage, and then there people seen some talent in me, and then some good people from the society keep on guiding me, and I get an opportunity to learn and I get an opportunity to study. So belonging from that kind of background and today teaching in one of the finest institute of this country to the topmost brains of this country, this is just like a dream come true. सो मेरे हिसाब से बड़ी ट्रमेंडस सक्सेस रही। सो मुझे कोई रिमोर्स नहीं है कि जो कुछ, ये तो सफ़र है, कुछ मंजिलें मिलती हैं और कुछ नहीं मिलती हैं। तो मुझे कभी ये था भी नहीं कि मुझे आईएएस ही बनना है या आईईएस ही बनना है। मैं तो गांव से निकला था सिर्फ इस सोच में कि 5-10 हज़ार रुपये महीने की लायक की कोई नौकरी लायक खुद को बना लूं तो जीवन आसान हो जाएगा, क्योंकि उस समय लाइफ वाज वेरी डिफ़िकल्ट इन द फैमिली। सो आई लेफ्ट इन माय विलेज इन 2002 आफ्टर 10th क्लास जस्ट विद दिस थॉट कि किसी तरह से इतनी पढ़ाई करना है कि 5-10 हज़ार रुपये महीने की भी अगर नौकरी मिल जाए तो जीवन थोड़ा सा आसान हो जाए। तो उस कंपैरिजन में तो जीवन ने बहुत कुछ दे दिया है। सो बिल्कुल भी रिमोर्स नहीं है, बिल्कुल भी चिंता नहीं है। आइए अब जरा इस बैंड को फिर से बनाते हैं। सो नाउ वी आर हैविंग फॉर द सॉलिड्स अ सीरीज ऑफ एनर्जी लेवल्स लाइक दिस। दीज आर द एनर्जी बैंड्स, लोअर वन जिन्हें आप बॉन्डिंग मॉलिकुलर ऑर्बिटल्स की तरह कंसीडर कर सकते हो, एंड दीज आर द एनर्जी लेवल्स हायर वन जिन्हें एंटी बॉन्डिंग की तरह कंसीडर कर सकते हो। मित्रों जरा एक चीज देखिए, जैसे ये सिलिकॉन है, ये सिलिकॉन है, ये सिलिकॉन है, ऑल दीज आर द सिलिकॉन एटम्स, ये सभी सिलिकॉन एटम्स हैं। All these are having 4 electrons. All these are having 4 electrons. ये सभी 4 इलेक्ट्रॉन कैरी कर रहे हैं, इन सभी के पास 4 इलेक्ट्रॉन्स हैं। All of them are carrying 4 electrons. सभी ने 4 इलेक्ट्रॉन कैरी किया है, ठीक। So they are bonding with each other. So all these valence electrons have participated in the bond formation. If we are at 0 Kelvin, let us suppose no thermal energy, no external energy is provided to this system. So this system is stable, this crystal is stable. So all these electrons which are in the valence band, they are in the bond. They have participated in the bond formation, right? This band of energy, you are saying it as valence band. It is valence band. The topmost energy level of valence band, this is designated as EV. EV is highest energy level of valence band. Highest energy level of valence band. It is the highest energy level of valence band. This range of energy, this is known as conduction band. This is known as conduction band. And the bottommost energy level of this conduction band, this EC. EC is lowest energy level of conduction band. Lowest energy level of conduction band. The gap between EC and EV, this is EG, and this EG is known as forbidden energy gap. This is known as forbidden energy gap. इसे forbidden energy gap कहा जाएगा. EG is equal to EC minus EV. Mathematically, इन दोनों के बीच का डिफरेंस ही forbidden energy gap कहा जाएगा. Now you see, if any electron is in valence band, it is bonded electron, and bonded electron is not free to move anywhere in the material. So such electrons which are in the valence band, they are in the bond, and bonded electron को हम लोग free electron नहीं कह सकते. And if they are not free electron, they will not be able to move throughout the material. And if they are not able to move throughout the material, they will not contribute into the current. So these valence electrons are not going to contribute into the current in an ordinary case. In a special case, they would be contributing, that I would be discussing later. But in general, the bonded electron is moving around two nucleus. So it is locally moving, and to get the current, the electron must move from one end of the material to the other end. So this electron cannot contribute into the current. How can we get current? We can get current if we supply energy so that this electron can reach to conduction band. It means if we supply energy greater than the band gap energy, then an electron will be moving from conduction band to the valence band. From where we can supply this energy? Let us suppose we put this material at room temperature. So room temperature will provide certain thermal energy, and if that thermal energy is sufficient, then this electron will be moving to the conduction band. Now one state in the conduction band will be occupied, and one state in the valence band will become empty. As soon as electron is reaching conduction band, what happens? Have a look. Let us suppose this electron occupies sufficient energy and this goes to the high energy state, that is known as conduction band. So as soon as this electron is leaving this position, a covalent bond is broken. So it means now this electron is not in the bond, so it has become free electron. So any electron which is in conduction band, that is free electron. This is not in the bond, and free electrons are able to move into the material. So the electrons which are reaching to the conduction band, they will be known as free electrons, and they are ready to move throughout the material. They are able to conduct electricity. That's why this band of energy is known as conduction band, because the electrons in this band of energy are not bonded to any atom. Instead, they are free to move throughout the material. So such electrons will contribute into the electricity. अब किसी मटेरियल का कंडक्टर या इंसुलेटर होना इस बात पर डिपेंड करेगा कि हाउ मच इलेक्ट्रॉन्स आर देयर इन द कंडक्शन बैंड. For any material, whether it is conductor or insulator, it will be decided on the basis of the fact that how many electrons has reached to the conduction band from valence band. Most of the material properties we judge at the room temperature. So material property, whether it is conductor or insulator, it will be decided that at room temperature how many electrons has moved from valence band to conduction band. If more number of electrons has moved into the conduction band, then material will have high conductivity and such materials will be known as conductor. But if very less electrons has moved to the conduction band, it means material has negligible conductivity and such materials will be known as insulators. So at room temperature, how many electrons will be moving towards the conduction band? This would be depend upon the band gap. If the band gap of the material is wide, then very less electrons would be moving, and if the band gap is narrow, then very high electrons would be moving. So this gap, forbidden energy gap Eg, will decide whether the material is going to be conductor or it is going to be insulator. My dear friend, this gap is what? This is difference between bonding and anti-bonding energy levels. This is the gap, easy, right? So if bond is very strong, it means atoms are coming very closer to each other, then attraction force and repulsion force will be very strong. So if attraction force is very strong, this energy level will go very down. And if repulsion force is very strong, this energy level will go up and this band gap would be wide. If attraction force is weaker, then this energy level cannot go much down, this cannot go much up, and this gap would be narrow. So stronger the bond, wider is the band gap, and weaker is the bond, narrower is the band gap. So band gap of the material will depend upon the strength of the bond. I told you ionic bond is the strongest one. It means in ionic materials you have wide band gap and metallic bond is the weakest one. So there is a high probability that in metallic bond gap will be least. So you can write band gap depends upon the strength of bonding. Energy band gap depends upon strength of bonding. Stronger the bond, wider is the band gap. Weaker is the bond, narrower is the band gap. So band gap of any material would be decided on the basis of strength of the bond. So the materials which are having very strong interatomic bonding, they will be trying to make a solid which is going towards the insulator. The materials which have weak bond, they are going towards making a solid which is going to be a conductor. We will be watching it later. But one more thing, suppose we increase the temperature. So if we increase the temperature, it means bonds will become weaker because you are supplying thermal energy, so lattice vibration will increase, and if lattice vibration is increasing, bond will become weaker, and if bond is weaker, band gap should become narrow. It means what? With increase in temperature, energy band gap decreases, because with increase in temperature, bond strength is decreasing, and if bond strength is decreasing, band gap is narrowing. So you can write this also. With increase in temperature, energy band gap, that is Eg, decreases. So from this discussion we can conclude that the material's behavior for the electrical force will be decided by this band gap. If this band gap is wide, then the material is having less probability of being conductor, and if it is narrow, then it is having wide probability of having conductivity. So we would be classifying material based upon the width of the band gap. But before that, you please write down this. So कृपया ऐसे लिख लें, ये ऊपर का आप लिख चुके हैं, यहाँ तक लिख लें. सो हम आगे चलते हैं. प्रतीक, मैंने आंसर दिया कि यहां हम ये मान लेते हैं कि एक स्पिन पर जो एक इलेक्ट्रॉन है वो एक सेपरेट एनर्जी स्टेट है और दूसरी स्पिन सेपरेट एनर्जी स्टेट है। तो जैसे किसी एक स्टेट पर दो इलेक्ट्रॉन हो सकते हैं, एक एंटी क्लॉकवाइज और दूसरा क्लॉकवाइज, दोनों को हमने सेपरेट स्टेट मान लिया है। नहीं बेटा, टू एंटी बॉन्डिंग और टू बॉन्डिंग हो गए तो स्ट्रक्चर ही नहीं बचेगा। हेमंत, I said that कि number of electrons in bonding must always be greater than number of electrons in anti-bonding. So there must be more electrons in the bonding. अगर आपने दोनों में इक्वल कर दिया तो बॉन्ड नहीं बन पाएगा, स्टेबिलिटी नहीं आ पाएगी। तो हमेशा बॉटम टू टॉप इलेक्ट्रॉन भरेंगे, तो पहले बॉन्डिंग वाली सारे भरेंगे, उसके बाद फिर एंटी बॉन्डिंग। Nista is asking, sir, my cousin is IAS 2020 batch electrical engineering from MEDG and she is preparing for IAS from next IAS online, so is better. Yes, no doubt IAS is better than IES, इसमें कोई डाउट ही नहीं। No dear, valence band is containing mainly valence electrons which are bonding electrons. Anti-bonding basically are in the conduction. Anti-bonding means high energy state. Money, we would be discussing it later. Once you once you qualify this examination for which you are preparing, then contact me. Then we would be discussing pros and cons of the optional taking technical. इतना संक्षिप्त आंसर देना ठीक नहीं है। Do it quickly. Yes, Mukul, you can say that. देखो यहाँ बॉन्डिंग एंटी बॉन्डिंग के बहुत चक्कर में मत पड़ो। बॉन्डिंग एंटी बॉन्डिंग इज फॉर मॉलिक्यूल्स ओनली, वी आर टॉकिंग अबाउट सॉलिड। आई सेड दैट कि दिस आई एम टेकिंग जस्ट टू एक्सप्लेन कि हाउ स्प्लिटिंग इज हैपनिंग। Attraction is leading towards the lower energy and repulsion is leading towards the higher energy. So always for the stability, the lower energy states should have more electron than the higher energy state. बिना मतलब bonding anti bonding पकड़े बैठे हुए हो, that's only for molecules. वहां से हम extend करके समझने की कोशिश कर रहे हैं for the solid. For the solids you have two bands, one lower energy and other higher energy. Between these two bands you have gap. Right? So lower energy states में जब तक ज्यादा इलेक्ट्रॉन रहेंगे than the higher energy states, till then the structure is stable. If higher energy state will have more electrons than the lower energy state, then structure will not be stable. तभी आपका solid liquid में convert हो जाता है. If all the bonds are broken and electrons go to the conduction band, then it will not remain solid, it will become unstable, it has become liquid, right? So the basic concept दिमाग में रखिए कि हमेशा for better stability of any system, energy should be minimum. energy can be minimum only if all the electrons are occupying the lower energy states. Lower energy states are what? Valence band. So in the valence band there are 4n states. Topmost states of all those 4n we are saying it as EB. ठीक? In conduction band also there are 4n states and bottommost states we are saying as EC. ठीक? So for stability, for the better stability, all the electrons must be in the lowermost. But as we keep on increasing the temperature, few of the electrons are getting energy from the temperature and they are moving towards the higher energy states, right? So until and unless very less electrons are in the higher energy state. Let us suppose you were having total 100 electrons. So out of 100 only 10, 5 are going here, no problem. 10, 20 are going here, no problem. But if 50 electrons go to the higher energy state, so remaining 50 will be in lower and 50 in the upper. Now your structure cannot be stable, because for the stability, number of electrons in the lower energy state must always be greater than number of electrons in the higher energy states. Then your solid will convert into liquid, it will not remain stable. So for the stability of solid, always there must be more electrons in the valence band rather than the conduction band. But if you are supplying temperature, few must be moving towards the conduction band. If you are at 0 Kelvin, no electron is going to the conduction band will remain empty state, so only electrons will be in the valence band, right? Next point. Heat transfer का concept अंकुश तेलमशारे we would be discussing when I would be teaching you conductor. Don't worry, अभी हम concept built up कर रहे हैं, थोड़ा सा patience रखिए, आप बिल्कुल confused नहीं होंगे. कीप पेशेंस. और इलेक्ट्रिकल का आदमी मैं हूं, तो जो मैं कहूंगा वही सत्य है. प्लीज कम टू द पॉइंट. क्लासिफिकेशन ऑफ मटेरियल्स. Classification of materials based upon energy band gap. Classification of materials based upon energy band gap. First, insulators. These are the materials which have very wide band gap. This is valence band. Top of the valence band EV, this is conduction band, bottom of the conduction band is EC, this is the band gap, that is EG. EG is greater than 3 electron volt minimum. उससे ज़्यादा कुछ भी हो सकता, 4, 5. Sometimes I used to write it approximately 5 electron volt. These materials are having very wide energy band gap. These materials are having very wide energy band gap, very wide energy band gap. Roughly around greater than 3 electron volt. Easy greater than 3 electron volt. Because of wide band gap, because of wide band gap, negligible electrons can reach to conduction band, can reach to conduction band. Therefore, conduction band remains almost empty, remains almost empty, almost empty. Hence, these materials are bad conductor of electricity, bad conductor of electricity, जिन्हें आप insulator कहते हैं, because they do not have free electrons. So who will provide conductivity? इनके कुछ examples अगर मैं देखूं, so there are certain popular examples of these insulators. One example is alumina. That is popularly, chemical formula is Al2O3. Sand, SiO2. Electrical porcelain, which is known as चीनी मिट्टी, electrical porcelain, China clay जिसे कहते हैं, that is also used as an insulator, etc. These are some popular insulators used in the industry. Please note down it. Congratulations, Salini. That's wonderful achievement. Good. Which branch? EC or electrical he was? Done? Right. Next one. Next one is semiconductors. These materials have narrow energy band gap. Narrow energy band gap. This is valence band and this is conduction band. So band gap is very narrow. Eg is roughly in the range of 1 electron volt. Because of narrow band gap, more number of electrons would be reaching to the conduction band. Hence, these materials will have better electrical conductivity than the insulators. But you will see later on that they will have less electrons as comparison to the conductors. So their electrical conductivity would be less than the conductors but greater than the insulators. So you would be writing these materials have very narrow energy band gap, very narrow energy band gap, energy band gap as compared to insulators, as compared to insulators. So these materials have higher electrical conductivity, than insulators, but less than that of conductors. कुछ important semiconductors जो हमारे पास हैं उनमें some important semiconductors are, for example, germanium. The band gap in germanium is 0.72 electron volt at room temperature. If you can remember, it's good. If you cannot remember, then you should know कि किसका ज़्यादा है किसका कम. Then other is silicon. The band gap in the silicon is 1.1 electron volt at room temperature. Third one is gallium arsenide. This is also very important semiconductor. Band gap is 1.4 electron volt. At least sequence to ध्यान रखो. There are several other semiconductors also, but we are interested in these three semiconductor materials. So these materials are having narrow energy band gap as comparison to the insulator. So they may have more number of electrons than the insulators. Hence their electrical conductivity would be greater as comparison to the insulators. सेमीकंडक्टर पढ़ेंगे तो सौर्य बात करेंगे इस बात पर. Ruchi is saying that, sir, is GS syllabus or PSC changes every year? No dear, they have not mentioned anything in GS syllabus. So it's the prerogative of teacher. We started from here. This is insulators. Semiconductor. The third one. If you recall, when I taught you metallic bonding, then I give one big statement. In metallic bonding, all the valence electrons are free to move anywhere in the material. So the electrons which are participating in the bond formation, they are also the free electron. Now you see, the electrons which are participating in the bond formation, I am saying them as valence band electrons, and the electrons which are participating in conduction, I am saying them as conduction band electrons. But in the metals, the electrons which participate in the bond formation, they are same which are free to move. It means metals are the materials in which there is no separate band. Valence band and conduction band overlap. एक ही बैंड है, उसी को आप बैलेंस बैंड कह दो या उसी को आप कंडक्शन बैंड कह दो. सो बिकॉज ऑफ मेटालिक बॉन्डिंग, बिकॉज आई टोल्ड यू कि रिमेनिंग टू बॉन्डिंग में क्या हो रहा, आयनिक या कोवैलेंट बॉन्डिंग में व्हाट इज हैपनिंग, one electron is going from one atom to another atom, या electron is shared between these two atoms. So bonded electron is between two atoms only. So it is not the free electrons. If you have to make this electron free, then you need to supply energy equal to the band gap. Basically you need to break the bond and then the electron would be free. But you see in the metallic bonding, what is happening, the electron which is in the electron cloud, that is participating in the bond formation, as well as that electron is free to move anywhere in the material. It suggests that in the metals, valence electron and free electron both are the same thing. All the valence electrons are free electrons. It means valence band and conduction band cannot be the separate things. Instead, both of them are the same. So there is no band gap. We have only one band, right? So third one is conductors. So in conductors, we are having a single band. This is the band we are having. So this band will have several energy states. इसे ही आप चाहे conduction band कह दें या valence band कह दें. Some of the bottommost states would be filled by the electron and some will be empty. So filled by electrons and empty of electrons. So there is no gap, there is no band gap. All these are in continuity. So these materials have energy gap Eg is equal to 0. Valence band and conduction band overlap. When you apply voltage, this electron will move anywhere in this empty states. other one will come into empty states, and this will keep on moving. So all these electrons are capable of moving throughout the material. So you have abundance of the electrons which can move into the material, hence these materials are very good conductor of electricity. So you can say that in these materials conduction band and valence band overlap. Conduction band and valence band overlap, and valence band overlap. That is, there is no energy band gap. There is no energy band gap. Eg is equal to 0. These materials are these materials are having large number of free electrons. So these are very good conductor of electricity. These are very good conductor of electricity. These are very good conductor of electricity. So these materials are very good conductor of electricity. Some of the examples of conductors are, all these metals are very good conductor of electricity. Some popular are, so first is Ag. Ag means silver, या सिल्वर ही लिख देता हूँ मैं, silver. It is the best electrical conductor. It is the best electrical conductor. Silver is the best electrical conductor. Then we have gold. That is another very good conductor. Second one is gold. Au. Then copper, that is Cu. Then aluminium, that is Al, etc. Copper is better conductor than aluminium, but aluminium is cheaper, so aluminium is very frequently seen to be used as conductor, although cost is the only thing which favor to the aluminium. Otherwise copper is better conductor than aluminium. So you can write copper is better conductor than aluminium, but aluminium is cheaper than copper, aluminium is cheaper than copper. ठीक है, एक छोटी सी बात करना, उसके बाद आप लिखिएगा. हमारे पास ये सेमीकंडक्टर है. In this semiconductor the band gap is very narrow. So whatever electrons move from valence band to conduction band, they become free electrons. So at temperature T1, let us suppose we have N1 free electrons, means electrons in the conduction band. If we increase temperature T2, T2 is increased temperature, then more number of electrons are reaching from here and the number of electrons is increasing. If T2 is greater than T1, then हमारे पास N2 is greater than N1. ठीक है? So in semiconductors, because of narrow band gap, when we increase the temperature, number of free electrons increases because some covalent bond would be broken and electrons would be reaching towards the conduction band. So you can write in semiconductors, with increase in temperature, number of free electrons increases. Free electrons कौन से होते हैं? The electrons which are in the conduction band. number of free electrons increases. ठीक, लेकिन लेट अस सपोज ये एक मेटल है, तो मेटल में जितने भी बैलेंस इलेक्ट्रॉन्स हैं, ऑल दोज आर फ्री, all the valence electrons are free. If it is a metal, so all the valence electrons are free. At any temperature, all the valence electrons are free electrons. Valence electrons are free electrons, are free electrons. In any temperature, all the valence electrons are free electrons. ठीक है, मेटल्स में। अब मेटल्स में अगर आप टेम्परेचर बढ़ा रहे हो, लेट अस सपोज T1 टेम्परेचर पर यू हैव n इलेक्ट्रॉन्स, सो ऑल दीज आर द n इलेक्ट्रॉन्स। नाउ सपोज यू इंक्रीज द टेम्परेचर, देयर इज नो पॉसिबिलिटी ऑफ गेटिंग मोर इलेक्ट्रॉन, क्योंकि जितने थे वो सारे के सारे क्या हो गए, फ्री हो गए। यहां ऐसा नहीं है, यहां बैलेंस में जो है ये ऊपर जाकर के फ्री बनाएंगे, ठीक, बट हियर वॉट एवर आर द बैलेंस इलेक्ट्रॉन दे हैव ऑलरेडी बिकम फ्री. So no matter what temperature you increase, you are going to get same number of electrons. So big conclusion is कि because of there is no band gap, so we can say that in metals with increase in temperature, with increase in temperature, with increase in temperature, there is no increase in number of free electrons. There is no increase in number of free electrons. Metals में टेम्परेचर इंक्रीज करने से फ्री इलेक्ट्रॉन की संख्या में कोई वृद्धि नहीं होगी. There is no increase in number of free electrons by increasing the temperature. Please note it down. Dear Apurva, you are making a quite illogical comparison. If these are discrete energy levels, so I said that closely spaced, but I didn't say that between two energy levels there is zero gap. There must be some negligible gap. Within a band, I am writing lines. These lines are what representing? They are representing the quantization, right? So energy is quantized even in the bands also. Sir, I am weak in computer organization and ESC technical COA and microprocessor. Did not make easy classes too. Kindly suggest me the best path for ESC 2022. Dear Nistha, 2023. Dear Nistha, even if you are weak in one or two subjects, I will say that please revise, please at least do the previous year questions of those subjects and focus on the remaining subjects in which you are strong. It's not necessary to attempt 100%. You have to maximize your attempt. So keep focus on those subjects where you are strong, make them more stronger. Although still there is a time left to cover the small subject like COA and microprocessor. So if you cannot cover it entirely, then at least from objective point of view try to cover it so that you can deal with the easy questions. So dear friends, from here this chapter would be classified in three broad units. First one conductor, second one semiconductor, and third one insulator. It will take at least more than 2 lectures. 2 lectures minimum it will take tomorrow and day after tomorrow to cover it. Even after that half of the lecture may be required. It is the lengthiest chapter we have. After that we would be finishing 1 chapter or 2 chapter in a lecture, sometimes 1 chapter, sometimes 2 chapters in a lecture, because after that the chapters are very small one. So today I am making the end of the class here, and tomorrow we would be taking the first topic, that is conductor, and conductor onwards we keep on discussing. Tomorrow we will be covering conductor and will be starting with the semiconductor. In the next class we will be covering semiconductor and will be trying to cover insulators as well. So at least 2 lectures would be required to cover these 3 topics. So this whole chapter will be divided in 3 groups: conductor, semiconductor, and insulator. We will be dealing with the conductor and semiconductor in tomorrow's class. Thank you. Have a wonderful time.